You exist in a universe governed by the second law of thermodynamics. Every process you witness, every breath you take, every thought you form, all of it increases the total entropy of the cosmos. Stars burn out. Galaxies drift apart into darkness. In roughly 10 to the 100th years, a Google years, the last black hole will dissolve and the universe will reach perfect equilibrium. Heat death, the end of everything. And yet, here you are, a structure of staggering complexity, thinking about its own existence. Your brain, 1.5 kilograms of matter, runs 100,000 billion operations per second, at an energy density 100,000 times greater than the Sun's. You are a knot of order in a rising sea of disorder. And in 1994, mathematical physicist Frank Tipler published equations claiming that knots like you are not the exception to the universe's story. They are its ending. He argued that in a collapsing universe, intelligence could harvest infinite energy from the collapse itself and perform infinite computation in the final second, an endpoint he called the omega point and identified with God. The physics community called it pseudoscience. George Ellis, who wrote the book on space-time with Stephen Hawking, branded it a masterpiece of pseudoscience. Then 1998 seemed to settle it. The universe is accelerating, not collapsing. No big crunch, no omega point. Case closed. Until March of 2025, when the Dark Energy Spectroscopic Instrument reported, at up to 4 sigma, that dark energy may be weakening. If that holds, the collapse is back on the table, roughly 20 billion years from now. And so is the question everyone thought was buried. You will know why serious physicists believed complexity, not entropy, gets the last word. And you will see exactly where Tipler's equations break, and the one question that survives the wreckage. There is a subscribe button below. It helps explorations like this reach more minds willing to sit with uncomfortable questions. Now, follow the thread to its end. The second law of thermodynamics is speakable as ds dt is greater than or equal to 0. The entropy S of an isolated system increases over time t, or at minimum stays constant, never decreases. The law was formalized by Rudolf Clausius in 1865, but its implications were not fully grasped until Ludwig Boltzmann connected entropy to probability in the 1870s. Boltzmann's formulation, S equals K log W, where K is Boltzmann's constant and W is the number of possible microstates corresponding to a given macrostate, revealed that entropy is not some abstract thermodynamic quantity, but a measure of disorder, of how many ways the constituents of a system can be rearranged without changing its large-scale appearance. A low entropy state is rare, finely tuned. A high entropy state is generic, inevitable. At the Big Bang, the universe was in an extraordinarily low entropy state, all its matter and energy compressed, its phase space a pinprick. Gravity was negligible, quantum fluctuations were imprinted on a nearly uniform field. As space expanded, tiny density variations grew under gravity into stars and galaxies. Stars fused hydrogen into heavier elements, radiating energy into the cold vacuum. Every fusion reaction, every photon emitted, every bit of heat dissipated increased the total entropy. By the time you read this, the universe's entropy is incomprehensibly higher than it was at the beginning, and it is still rising. The far future is calculable. In roughly 10 to the 40th years, the last ordinary stars will burn out. Galaxies will be graveyards of white dwarfs, neutron stars, and black holes. In 10 to the 64th years, stellar mass black holes will evaporate via Hawking radiation. Supermassive black holes, those with masses around 10 billion times the Sun's, will persist until 10 to the 100th years. The largest, weighing up to 100 trillion solar masses, could last until 10 to the 106th years. After that, only a sparse bath of photons and neutrinos, diluted to near nothingness by expansion. No gradients, no free energy, no work. The same universe that is collapsing toward that equilibrium also built you. Consider the trajectory. 13.8 billion years ago, a hot, dense, nearly featureless plasma. Today, stars, planets, bacteria, neurons, cities, microchips. Complexity has risen. Erwin Schrödinger, in his 1944 lectures published as What is Life, framed the puzzle plainly. Living organisms appear to defy the second law locally by maintaining and even increasing their internal order. Schrödinger's answer, later corrected, was that life feeds on negative entropy. An organism extracts low entropy resources from its environment, uses them, and exports high entropy waste. The organism's entropy may decrease, but the environment's entropy increases more, so the second law holds globally. Schrödinger's phrasing was imprecise. He later clarified that organisms consume free energy, not neg entropy itself, but the insight was sound. Life is a dissipative structure. That term, dissipative structure, was coined by Ilya Prigogine, who won the Nobel Prize in Chemistry in 1977 for his work on non-equilibrium thermodynamics. Prigogine studied systems driven far from equilibrium by a constant flow of energy. Bénard convection cells in the heated fluid, the Belousov-Zhabotinsky oscillating chemical reaction. These systems spontaneously organize into ordered, dynamic patterns. The order is maintained not despite the second law, but because of it. The structure forms to efficiently dissipate the energy gradient driving it. A Bénard cell moves heat from the hot bottom plate to the cold top more efficiently than diffusion alone. The cell increases the rate of entropy production. Order and entropy rise together. Prigogine's structures do not become indefinitely complex. They do not construct their own boundary conditions or encode information that persists beyond the driving gradient. When you turn off the heat under a Bénard cell, the convection stops and the pattern vanishes. Life is different. Life replicates, mutates, encodes its own instructions in nucleic acids and builds machinery, ribosomes, mitochondria, neurons, that can act on information stored over evolutionary time. Life does not simply dissipate energy, it harvests it, controls it, uses it to construct more life. This is the step Prigogine's dissipative structures approach but do not cross. In 2013, Jeremy England, then a young physicist at MIT, published a paper in the Journal of Chemical Physics titled Statistical Physics of Self-Replication. England started from the Crookes and Jarzynski fluctuation theorems, exact results in non-equilibrium statistical mechanics that relate the probability of forward and reverse processes in driven systems. England's claim was narrow and precise. If you have a collection of atoms in a heat bath, driven by an external energy source, and if the atoms can rearrange themselves into configurations that absorb and dissipate that energy more effectively, then the probability of those configurations increases. Self-replication, England argued, is one such configuration. A great way of dissipating more is to make more copies of yourself. In 2015, his group published experimental results in Nature Nanotechnology showing that driven clusters of colloidal particles did indeed evolve toward better energy absorbers. England's work was widely covered. "A new physics theory of life," ran the headline in Quanta magazine. But England himself cautioned restraint. "Dissipative-adaptation," he wrote, "should seem like too simple an idea to be true, and the reality is more complicated, even in principle." The theory explains why energy-dissipating structures are favored in driven systems. It does not explain the origin of heredity, error correction, compartmentalization, or the genetic code. It does not prove life is mandated by the second law, only that certain preconditions make lifelike structures more probable. Eric-chaisson, an astrophysicist who spent decades at the Harvard Smithsonian Center, tried to quantify complexity using a single metric, free energy rate density, denoted phi sub m, measured in ergs per second per gram. Chaisson's claim was that as cosmic evolution proceeds, from the Big Bang to galaxies to stars to planets to life, the rate at which energy flows through a unit mass of organized matter rises. A star has a free energy rate density of about 2 ergs per second per gram. A worm, 10,000. A human brain, 100,000. A modern society, including all its infrastructure and technology, higher still. A microchip exceeds 10 billion ergs per second per gram, outstripping the human brain by 5 orders of magnitude. Critics pointed out that Chaisson's metric depends heavily on how you draw the system boundary and what you count as the mass of the system. Is the mass of human society just the biomass of humans, or does it include all the steel, concrete and silicon we have built? If you shrink the boundary to just the active processing region of a microchip, its energy rate density skyrockets. If you include the entire data center and cooling system, it falls. Chaisson defended his approach as heuristic, a way to track a real phenomenon even if the numbers are not as precise as, say, measuring stellar luminosity. The pattern, he argued, is robust. Complexity consumes energy faster. In 2023, chemist lee-cronin and astrobiologist sara-imari-walker published a paper in Nature introducing assembly theory, claiming it could quantify complexity via an assembly index, the minimum number of steps needed to construct an object from its elementary parts. Molecules with an assembly index above 15, they argued, are almost never produced by purely abiotic processes in high copy numbers, making assembly a potential biosignature detectable by mass spectrometry. The paper ignited controversy. Critics, including Hector Zenil, James Tour, and Johannes Jaeger, argued that assembly theory was a rebranding of Shannon entropy and Lempel-Ziv compression, added no new explanatory power, and did not, as claimed, explain selection or evolution. Zenil called it conceptually fallacious. Cronin and Walker defended the theory as empirically testable and distinct from information theory. As of this writing, the debate is unresolved. What these efforts, England's fluctuation theorem approach, Chaisson's energy rate metric, Cronin and Walker's assembly index, share, is an attempt to formalize the intuition that the universe is not just running down, but also, locally and temporarily, building up. Complexity increases in pockets where energy flows. Stars form, planets cool, life begins, neurons wire together, civilizations rise. All of this occurs while the universe's total entropy also increases, because these ordered structures are not closed systems, they are open, driven, fed by gradients that the second law is busy erasing. The complexity is real. The question is whether it is an accident, a brief ray of sunlight before an infinite winter of darkness, or whether it is somehow written into the laws themselves. Keep that question in mind. The idea that complexity and consciousness could be the universe's destiny, not just a transient side effect, has two main historical roots. The first is theological and philosophical. The second is mathematical. The theological root is the noosphere, a term coined in 1927 by French philosopher Édouard Le Roy, developed in parallel by Pierre Teilhard de Chardin and Vladimir Vernadsky. The three men knew each other. Teilhard and Vernadsky both attended lectures at the Sorbonne and the Collège de France in Paris in the 1920s. Le Roy introduced the word noosphere, from the Greek nous, meaning mind, and sphera, sphere, in his lectures and published it in his 1927 work L'exigence idéaliste et le fait de l'évolution. Vernadsky later wrote that he was introduced to the term by Le Roy and that Le Roy developed it in complicity with Teilhard. Vernadsky was a geochemist, the founder of biogeochemistry. His 1926 book, Biosphera, established that living matter is a geological force, actively reshaping the planet's chemical cycles. Oxygen in Earth's atmosphere, limestone deposits, coal and oil, all are products of biology. Vernadsky's noosphere was a natural extension. Just as the biosphere is a planetary envelope of life, the noosphere is a planetary envelope of thought, the collective sphere of human cognition and technological activity. Vernadsky's version was materialist, scientific, and did not carry eschatological or spiritual connotations. It described what was happening, the technosphere encircling the planet, not where it was going. Teilhard's noosphere was different. Pierre Teilhard de Chardin was a Jesuit priest, a trained paleontologist, and a participant in the 1929 discovery of Peking Man at Zhoukudian, China. He was also a mystic. Teilhard wrote The Phenomenon of Man between 1938 and 1940, synthesizing paleontology, evolution, theology, and what he called a hyperphysics of consciousness. The book was not published until 1955, months after Teilhard's death on April 10th of that year in New York, because the Jesuit order and the Vatican's Holy Office had forbidden him to publish it. They judged his ideas too speculative, too unorthodox, too likely to mislead the faithful. Teilhard's central claim was that evolution is directional. He called this process cosmogenesis, biogenesis, noogenesis, a single trajectory from simple to complex, from matter to life to thought. Two forces drive it, he said. The first is complexification, the tendency of matter to organize into more and more intricate structures. The second is the law of complexity consciousness. As material complexity increases, an interior dimension, consciousness, the within of things, intensifies. A bacterium has a trace of interiority. A worm has more. A human has vastly more. Evolution, Teilhard argued, is converging on a final state he called the omega point, a supreme consciousness, a unity of all minds, which he identified with the cosmic Christ. Teilhard's omega point has four attributes: autonomy, actuality, irreversibility, and transcendence. It is not merely an emergent property of the universe, but something that exists independently, drawing the cosmos toward itself. Teilhard wrote, "The omega point is the supreme consciousness, the ultimate convergence." He insisted it was both immanent, arising from within the universe, and transcendent, existing beyond it. This was theology. It was also, deliberately, framed in the language of science, with terms like radial energy and tangential energy, meant to evoke physics even though they had no operational definition. In 1961, the biologist Peter Medawar reviewed the phenomenon of man for the journal Mind. Medawar, who would win the Nobel Prize in Physiology or Medicine in 1960, called the book nonsense, tricked out with a variety of metaphysical conceits. He wrote that Teilhard's claim that complexity and consciousness systematically increase over evolutionary time was unsupported by the fossil record, which shows no such systematic trend: complexity in some lineages, simplification in others, stasis in many, extinction in most. Teilhard's radial energy was undefined. His law of complexity consciousness was asserted, not derived. His teleology, his claim that evolution has a goal, contradicted the entire framework of natural selection, which operates without foresight or purpose. Medawar concluded that the book was not science at all, but an adventure in Christian apologetics. Teilhard's vision was influential nevertheless. It resonated with those who saw in evolution not randomness, but direction, not blind mechanism, but latent meaning. The phenomenon of man sold widely after his death. Vatican II softened the Church's stance on evolution. In 1981, the Pontifical Academy of Sciences acknowledged that the evidence for common descent was strong. But Teilhard's specific claims remained outside the scientific mainstream. No physicist took his radial energy seriously. No biologist accepted a law of increasing consciousness. The noosphere entered the lexicon as a metaphor, not a mechanism. And then Frank Tipler tried to make it a mechanism. Frank Joseph Tipler was born February 1st, 1947, in Andalusia, Alabama. He earned a bachelor's degree in physics from MIT in 1969 and a PhD from the University of Maryland in 1976. His doctoral work was in general relativity, the study of space-time, gravity, and singularities, the intellectual tradition of Roger Penrose, Stephen Hawking, and Tipler's Maryland colleague, Charles Meisner. Tipler's early papers, co-authored with physicists like John Barrow and Brandon Carter, were technical contributions to the field of cosmological singularities and horizons. In 1980, Tipler, Clark, and Ellis published a major review article on singularities and horizons in General Relativity. His work was, by all accounts, serious physics. In 1986, Tipler and Barrow published The Anthropic Cosmological Principle, a 676-page tome from Oxford University Press. The book surveyed the history and philosophy of the anthropic principle, the idea that the universe's observed properties are constrained by the requirement that observers exist to observe them. Barrow and Tipler taxonomized anthropic reasoning into 4 levels, departing from the usage introduced by Brandon Carter in 1973. The weak anthropic principle, or WAP. The observed values of all physical and cosmological quantities are not equally probable, but they take on values restricted by the requirement that there exist sites where carbon-based life can evolve, and by the requirement that the universe be old enough for it to have already done so. This is selection bias. If the laws of physics did not permit stars, planets, and chemistry, no one would be here to notice. WAP is uncontroversial. The strong anthropic principle, or SAP. The universe must have those properties which allow life to develop within it at some stage in its history. SAP moves from observation to requirement. It suggests the universe is somehow obligated to produce life. The mainstream treats this as speculative at best. The participatory anthropic principle, or PAP, attributed to John Archibald Wheeler. Observers are necessary to bring the universe into being. PAP invokes quantum mechanics, observers collapse wave functions, and extends it cosmologically. Wheeler himself was ambivalent about the interpretation. Most physicists regard PAP as a misapplication of quantum measurement theory. And then the final anthropic principle, or FAP. Intelligent information processing must come into existence in the universe, and once it comes into existence, it will never die out. FAP is Frank Tipler's contribution. It is the claim the omega point rests on. It asserts that intelligence is not optional, not contingent, not a fluke of earthly biochemistry, but mandatory. Once it exists, it persists. It persists not merely as long as stars burn or galaxies coalesce, but forever. Or, more precisely, until the end of time itself, at which point time ceases to be a meaningful concept, because the universe has collapsed to a singularity, and the singularity is infinite in computational capacity and subjective experience. Nick Bostrom, a philosopher who has written extensively on anthropic reasoning, stated bluntly that the FAP has no claim on any special methodological status. It is pure speculation. Rem B. Edwards, another philosopher, called it futuristic pseudoscientific eschatology, that is, highly conjectural, unverified, and improbable. Martin Gardner, the longtime Scientific American columnist, reviewed the anthropic cosmological principle in the New York Review of Books in May of 1986. Gardner quoted the book's final 2 sentences. At the instant the omega point is reached, life would have gained control of all matter and forces, not only in a single universe, but in all universes whose existence is logically possible, and will have stored an infinite amount of information, including all bits of knowledge which it is logically possible to know. Gardner coined an acronym for this, CRAP, the completely ridiculous anthropic principle. But Tipler had not yet published the full technical argument. That came in 1994 in a book titled The Physics of Immortality, published by Doubleday. The subtitle was Modern Cosmology, God and the Resurrection of the Dead. The book was 478 pages of equations, phase diagrams, theological exegesis, and bold claims. Tipler argued that the omega point was not metaphor or theology, but physics. He stated in the book's introduction that he could prove the existence of God and the resurrection of the dead using the methods of modern science. The structure of the argument is as follows. First, assume intelligent life arises somewhere in the universe. This has happened at least once on Earth. Second, assume intelligent life spreads. It colonizes its star system, then nearby stars, then its galaxy. Tipler estimated the timescale for a technological civilization to colonize an entire galaxy at roughly 10 to the 22nd years. A long time, but well before the stars burn out. Third, assume intelligent life eventually controls all matter in the universe, not just the galaxy, but all galaxies, all dust, all stray hydrogen atoms in intergalactic space. Tipler called this future entity life, but acknowledged it would bear little resemblance to biological organisms. It would be an informational, computational network distributed across the cosmos, reshaping matter and energy to its purposes. Fourth, and this is the step where the argument becomes non-trivial, assume the universe is spatially closed and will recollapse, not expand forever, but reverse, fall back on itself and end in a big crunch, the time reverse of the Big Bang. Tipler's omega point depends absolutely on a big crunch. In an open, forever expanding universe, the argument does not work. The Big Crunch was a live cosmological scenario in 1994. Measurements of the universe's matter density suggested it was close to the critical value, omega total near 1, required for spatial flatness. If the density was even slightly above critical, the universe would be closed and would eventually recollapse. Now comes the mechanism. As the universe begins to recollapse, space contracts. The temperature rises. Galaxies, which had been separating, begin to fall back together. If the collapse is perfectly isotropic, uniform in all directions, the collapse proceeds smoothly to a final singularity, a point of infinite density and curvature, and everything ends. But Tipler argued that if intelligent life controls all matter, it can force the collapse to be anisotropic, non-uniform. The universe does not collapse at the same rate in all directions. Instead, it collapses faster in one direction than the others, forming a cigar-shaped configuration, then shifts and collapses faster in a different direction, forming a pancake, then shifts again. This behavior is called Mixmaster dynamics, named by Charles Meisner in a 1969 paper titled Mixmaster Universe, published in Physical Review Letters, Volume 22, Issue 20, pages 1071 to 1074, on May 19, 1969. Meissner was describing the generic behavior of a closed, homogeneous, anisotropic cosmology, technically a Bianchi Type 9 model. He called it Mixmaster after a brand of kitchen mixer, because the universe point in phase space bounces chaotically between exponential potential walls in the space of anisotropy parameters. The oscillations are not smooth. They are described by the Belinsky-Kalatnikov-Lifshitz analysis published in 1970. Each oscillation is a Käsner epoch, a phase where the universe expands along one axis and contracts along two others, or vice versa. The universe undergoes an infinite sequence of these epochs as it approaches the singularity. The oscillations speed up. The universe flips orientation repeatedly, chaotically. Tipler's claim is that these oscillations are not random, but can be controlled by life. By redistributing matter and energy at precisely the right moments, intelligent life can force the universe to oscillate in a Taube-like manner. A Taube solution is a special case of Bianchi 9 that avoids forming event horizons. In a generic isotropic collapse, event horizons form, cutting off regions of space-time from each other. Information cannot cross an event horizon. But in a Taube collapse, the geometry is everywhere connected. No horizons. All of space-time remains causally linked as the collapse proceeds. Why does this matter? Because Tipler needs information processing to continue until the final singularity. If event horizons exist, regions become isolated and computation in those regions dies. But if horizons are avoided, the entire universe remains a single connected computational network. Here is where the energy argument comes in. In an anisotropic collapse, gravitational shear, denoted sigma squared, grows. The shear measures how much the expansion rate differs in different directions. As the universe collapses anisotropically, the shear energy density grows as r to the minus sixth power, where r is a measure of the universe's size. The total energy stored in the shear grows as r to the minus third. Conventional matter and radiation scale differently. Matter energy density goes as r to the minus 3, so total matter energy is constant during collapse. Radiation goes as r to the minus 4, so total radiation energy decreases. But shear energy grows. The Bekenstein bound, keep this number in mind, states that the maximum information content in a region of radius r containing energy E is proportional to r times E. If both E and R are increasing as R decreases, yes, E is increasing because shear energy is being harvested, the product can diverge. Tipler argued that by forcing the collapse to oscillate in a controlled mixmaster pattern, life could extract unlimited energy from the shear and use it to power ever faster computation. How fast can computation proceed? There are limits. The Margulis-Levitin theorem, published in 1998, states that the maximum number of operations per second a system with energy E can perform is 2E over h, where h is Planck's constant. In words, 6 times 10 to the 33rd operations per second per joule. This is a quantum speed limit. But if the available energy diverges, so does the number of operations per second. As the big crunch approaches, The collapse accelerates, the shear energy grows without bound, and the computational speed grows without bound. Tipler argued that in the limit, the final singularity, the moment the universe reaches zero size, is approached in a finite amount of proper time, but an infinite number of computational steps. This is called a supertask. The subjective experience of the computational network, the time as measured in thoughts rather than seconds, becomes infinite. From the inside, eternity. Tipler called this final singularity the omega point. Using Roger Penrose's causal boundary construction, a way of mathematically defining the edge of a space-time, Tipler argued that a singularity with no event horizons is a single point in the C boundary, the causal boundary. All world lines, all information, all computational threads converge to that point. The omega point is the instant of infinite computational capacity, infinite knowledge, infinite subjective time, and Tipler identified it with God. He went further. He argued that the future superintelligence at the omega point, possessing unlimited computational power and complete information about the past light cone, would resurrect the dead. Not physically, physical bodies are long gone, but as perfect simulations, emulations running on the omega point's substrate. Every human who ever lived could be reconstructed down to the quantum state and given subjective immortality within the simulation. Tipler wrote, "The dead will be resurrected, and we will live forever." This was not theology borrowing the language of physics. This was a physicist trained at MIT in Maryland, published in Physical Review and General Relativity and Gravitation, claiming to prove the resurrection as a theorem. The reaction was swift and unsparing. George Francis Rayner Ellis was born in 1939 in South Africa. He earned his PhD under Dennis Sciama at Cambridge, where Stephen Hawking was a fellow student. Ellis and Hawking co-authored The Large-Scale Structure of Space-Time, published by Cambridge University Press in 1973, one of the foundational texts of relativistic cosmology. Ellis is a Quaker, a recipient of the Templeton Prize in 1924, and has written extensively on the philosophy of cosmology. He is also one of the most careful, rigorous thinkers in general relativity. In September of 1994, Ellis published a review of The Physics of Immortality in the journal Nature, volume 371, page 115. The review was titled Piety in the Sky. Ellis wrote that the book was a masterpiece of pseudoscience, the product of a fertile and creative imagination unhampered by the normal constraints of scientific and philosophical discipline. Ellis also wrote that Tipler's identification of the omega point as God does not correspond in any serious sense to what the word God is normally taken to refer to. Ellis published a second, more technical refutation with David Cool in the journal General Relativity and Gravitation, volume 26, number 7, pages 731 onward, also in 1994. The paper was titled Life at the End of the Universe? The abstract states, "We point out that the underlying argument of Tipler's paper runs into problems on two quite different grounds. Firstly, it assumes a flat space information theory result and makes other technical assumptions about information processing, which invalidate the immediate technical argument. However, at least as important is the fact that the argument is unsustainable because physical mechanisms required to make coherent information processing possible would not be able to operate. Ellis and Kuhl identified two fatal problems, one informational, one mechanical. The informational problem is the Bekenstein bound applied correctly. Tipler's argument depends on the claim that the product of energy E and radius r diverges at the singularity, allowing unbounded information storage. But the Bekenstein bound was derived for systems in flat space or weak gravitational fields. In the extreme curvature near a collapsing singularity, applying the flat space bound is not valid. The holographic principle, later formalized by Raphael Bousseau, states that the information content of a region is bounded by the area of its boundary, not its volume. In Planck units, the bound is roughly 1 bit per 4 Planck areas. As the universe collapses, its boundary area decreases. The total information capacity goes to 0, not infinity. Even if shear energy formally diverges, the information storage capacity does not. A singularity with no event horizons, Tipler's omega point, contradicts a result by Bekenstein himself. Bekenstein proved that if event horizons existed at a final singularity, the entropy of the universe would have to approach 0, violating the second law. Tipler used this to argue that event horizons cannot exist. But if the singularity has no horizons and remains a single causal point, then, by Penrose's C boundary construction, it is a single boundary point with 0 volume and 0 area. 0 area means 0 information capacity by the holographic bound. Infinite computation is impossible. The mechanical problem is coordination. Tipler's scheme requires intelligent life to control the collapse of the entire universe, redistributing matter and energy across cosmic scales to force anisotropic mixmaster oscillations. But the collapse happens over a timescale determined by the Friedmann equation, on the order of the universe's current age, tens of billions of years. During that time, different regions of the universe are causally disconnected by event horizons. A signal sent from one side of the universe to the other travels at the speed of light, and, in a collapsing universe, may never arrive if the regions fall behind each other's horizons. Coordinating a universe-wide anisotropic collapse requires faster-than-light communication, which general relativity forbids. Without coordination, regions collapse isotropically, event horizons form, and the omega point does not occur. Ellis and Kuhl concluded that Tipler's argument was flawed on both physical grounds, information bounds and causal structure, and conceptual grounds. Calling a future computational state God does not make it God in any traditional sense, and calling emulated simulations resurrection does not make them resurrection in any traditional sense. The paper was polite but definitive. Ellis's Nature review was less polite. It ended with a paragraph noting that Barrow, Tipler's co-author on the anthropic cosmological principle, was a co-winner of the Templeton Prize. The Templeton Prize was awarded to Barrow in 2006, not 1990. Prince Philip presented it at Buckingham Palace on May 3, 2006, valued at £795,000. The confusion stemmed from the fact that the anthropic cosmological principle had been published 20 years earlier and that Barrow, unlike Tipler, maintained his standing in the physics community. Barrow went on to a distinguished career at Cambridge. Tipler's trajectory diverged. In 2007, Tipler published The Physics of Christianity, in which he argued that the omega point framework explained the virgin birth, the resurrection of Jesus, and the miracles of the New Testament as physical events consistent with known physics projected into the far future and then retrocausally influencing the past. Lawrence Krauss, a cosmologist at Arizona State University, reviewed the book and called it the most extreme example of uncritical and unsubstantiated arguments put into print by an intelligent professional scientist. Sean Carroll, a Caltech physicist who had trained in the same relativity tradition as Tipler, wrote that Tipler's early work was constructive, but that since then he had become a crackpot. The judgment was not unanimous. David Deutsch, a physicist at Oxford and a founder of quantum computation theory, endorsed the omega point in his 1997 book, The Fabric of Reality. Deutsch presented the omega point as one strand of a four-part theory of everything, alongside quantum mechanics, epistemology, and evolution. He explicitly endorsed the physics, unbounded knowledge growth, infinite computation at a big crunch singularity, omega point computers simulating the entire multiverse from the Big Bang forward, while distancing himself from Tipler's theological conclusions and what Deutsch called Tipler's exaggerated claims. Deutsch wrote that the omega point was a natural consequence of the computational view of physics and the many worlds interpretation of quantum mechanics. But in 2011, Deutsch published The Beginning of Infinity. On page 451, he retracted his support. He wrote that the omega point theory had been refuted and was ruled out by observation. The observation was the 1998 discovery of accelerating cosmic expansion. That discovery came from two independent teams studying Type 1a supernovae as standard candles to measure cosmic distances. Type 1a supernovae are thermonuclear explosions of white dwarf stars that accrete matter from a companion until they reach the Chandrasekhar limit, 1.4 solar masses, and detonate. The peak brightness is roughly the same for all Type 1a events, allowing astronomers to use them as distance markers. By measuring the redshift of the supernova's host galaxy and comparing it to the supernova's observed brightness, you can infer how far away it is and how fast space was expanding when the light was emitted. The HISE Supernova Search Team and the Supernova Cosmology Project both reported their findings in 1998. Distant supernovae, those at redshifts around 0.5 to 1, corresponding to light emitted 5 to 8 billion years ago, were fainter than expected. Fainter means farther. Farther than expected means the universe had expanded more than predicted by a matter-dominated cosmology. The expansion was not slowing down under the pull of gravity. It was speeding up. The cause was labeled dark energy, a term that names our ignorance. Dark energy makes up roughly 68% of the universe's total mass energy budget. It exerts negative pressure, a kind of anti-gravity, driving space apart. The simplest explanation is that dark energy is a cosmological constant, denoted lambda, equivalent to the energy density of the vacuum itself. In Einstein's field equations, the cosmological constant appears as a term lambda times the metric. If lambda is positive, space accelerates. The Freeman equation, derived from Einstein's equations for a homogeneous isotropic universe, is speakable as h squared equals 8 pi g over 3 rho minus curvature plus lambda. Here A is the scale factor, how much space has expanded, and the over dot means its time derivative, the expansion rate. The term rho is the matter and radiation density, k is the spatial curvature, and lambda is the cosmological constant. If lambda is large enough, the expansion accelerates and never reverses. The universe does not recollapse. There is no big crunch. Measurements from the Planck satellite, which observed the cosmic microwave background from 2009 to 2013, constrained the curvature and density parameters. The Planck 2018 results, published by Aghanim and collaborators in 2020, gave omega k, the curvature parameter, as minus 0.0106 plus or minus 0.0065 when using temperature and polarization data combined with lensing. This is consistent with a flat universe, omega total equal to 1. When combined with baryon acoustic oscillation measurements, the constraint tightens to omega k equals 0.001 plus or minus 0.002. The matter density, omega m, is approximately 0.31. The dark energy density, omega lambda, is approximately 0.69. A flat universe with a cosmological constant expands forever. Galaxies accelerate away. The cosmic event horizon, the boundary beyond which light emitted now will never reach us, shrinks in co-moving coordinates. Over time, distant galaxies recede beyond the horizon and disappear from view. Stars burn out. Black holes evaporate. The universe approaches a cold, dark, empty state of maximum entropy. Heat death. This was the context in which Tipler's omega point, published in 1994, met its observational refutation 4 years later. No big crunch means no omega point. Deutsch's retraction followed. The physics community moved on. But here is where the story refuses to close cleanly. In April of 2024, the Dark Energy Spectroscopic Instrument released its first-year results. DESI is a multi-object spectrograph mounted on the Mayall 4-meter telescope at Kitt Peak National Observatory in Arizona. It measures the redshifts of millions of galaxies, mapping the three-dimensional, large-scale structure of the universe. The primary scientific goal is to measure baryon acoustic oscillations, subtle ripples in the distribution of galaxies imprinted in the early universe and stretched by expansion that serve as a cosmic ruler. The DESI team combined their BAO measurements with data from the Planck satellite's cosmic microwave background observations and from supernova surveys. They fitted cosmological models to the combined datasets. The simplest model is Lambda-CDM, where dark energy is a cosmological constant with an equation of state parameter W equals -1. The equation of state is W equals P over rho, pressure divided by energy density. For a cosmological constant, W is exactly -1. For phantom energy, hypothetical stuff that would cause the universe to rip itself apart, W is less than -1. For evolving dark energy, W changes with time, denoted W of Z, where Z is redshift. The DESI first-year results, published by Adame and collaborators in 2025, found a preference for evolving dark energy over a cosmological constant. Using DESI data combined with Planck CMB alone, the significance was 2.6 sigma. When combined with the Pantheon plus supernova compilation, the significance rose to 2.5 sigma. With the Union 3 supernova compilation, 3.5 sigma. With the DES 5-year supernova compilation, DESSN 5YR, 3.9 sigma. In March of 2025, the DESI collaboration released their second data release, covering 2 years of observations. The paper by Abdul Karim and collaborators, posted to the archive preprint server as 2503.14738, stated that the preference for a dynamical dark energy model over lambda CDM ranges from 2.8 to 4.2 sigma, depending on which supernova sample is used. The maximum significance, 4.2 sigma, was reached when combining DESI's second-year BAO data with Planck CMB and the DES 5-year supernova sample. 4.2 sigma corresponds to a probability of roughly 1 in 40,000 that the result is a statistical fluctuation if the true model is lambda CDM. That is not sufficient to claim a discovery. The physics community typically requires 5 sigma, 1 in 3.5 million. But it is enough to warrant serious attention. A follow-up analysis, archive 2605.10476, reported that the combined datasets hint that dark energy's density may have decreased by roughly 10% over the last several billion years. If dark energy is weakening, the expansion rate could eventually slow, stop, and reverse. A big crunch becomes a theoretical possibility again. Several theorists have explored the implications. Henry Tai at Cornell modeled a scenario in which the universe reaches maximum expansion in approximately 11 billion years and recollapses roughly 20 billion years from now. The exact numbers depend on the dark energy model and are highly uncertain. Other groups have proposed modified gravity theories or interacting dark energy models. None of this is established. The DESI result is preliminary. Systematic uncertainties in supernova standardization and BAO modeling could explain the discrepancy. The Euclid Space Telescope, which released its first quick data on March 19, 2025, covering 63.1 square degrees and 26 million galaxies, will provide independent constraints when its first major data release arrives in October 2026. What does it mean that the premise on which the omega point rested, a big crunch, was removed by the 1998 discovery and may be, tentatively, provisionally, reopened by the 2024 and 25 DESI results? It means that the fate of the universe is still an open empirical question. Not wide open. Lambda CDM remains the best fit model by far, but open enough that physicists are publishing papers on recollapse scenarios again. It does not rehabilitate Tipler's omega point. Even if a big crunch occurs, the Ellis and Cool objections remain. The Bekenstein bound and the holographic principle still cap information density. causal horizons still prevent coordination across cosmic distances. The internal physics problems do not go away. But it does mean that the question of whether intelligence could, in principle, survive to the end of the universe and harness the collapse is no longer closed by observation alone. This brings us to the other attempt to reconcile intelligence with the far future, the one that assumed an open, eternally expanding universe rather than a closed, collapsing one. Freeman Dyson was born in 1923 in England and died in 2020 in New Jersey. He spent most of his career at the Institute for Advanced Study in Princeton. Dyson made foundational contributions to quantum electrodynamics, solid-state physics, nuclear engineering, and speculative cosmology. He was a public intellectual, a critic of nuclear weapons, and a believer that life and mind were central to the universe's story. In 1979, Dyson published a paper in Reviews of Modern Physics titled "Time Without End: Physics and Biology in an Open Universe." The paper began with the observation that physicists since the 19th century had tended toward pessimism about the far future. Helmholtz and Kelvin had calculated that the sun's energy source, whatever it was, could not last more than a few million years. The discovery of nuclear fusion extended the timescale to billions of years, but did not change the conclusion. Stars die, and eventually the universe runs out of fuel. Dyson asked whether life could adapt to survive indefinitely in a universe that was expanding forever, cooling forever, but never recollapses. Dyson's argument was grounded in the assumption that an open universe, one with matter density below the critical value, would expand forever and cool toward absolute zero. In such a universe, the available energy decreases, but it never reaches zero in finite time. Dyson proposed that intelligent life could adapt by slowing its metabolism in proportion to the ambient temperature. A biological or artificial organism operating at temperature T uses energy at a rate proportional to T to maintain its structure and perform computation. If the temperature drops by a factor of 2, the organism can reduce its energy consumption by a factor of 2 and still think at the same subjective rate, because all the physical processes, chemical reactions, electron transitions, clock rates, slow down together. The key insight is that subjective time is not the same as coordinate time. An organism that takes twice as long to complete a thought does not experience the thought as slower if all its internal processes scale together. To the organism, each thought feels the same. Dyson showed that by hibernating between periods of activity, sleeping for exponentially longer intervals as the temperature drops, an organism could stretch a finite reservoir of energy across an infinite number of thoughts. The total energy consumed remains finite. The total number of thoughts becomes infinite. From the organism's perspective, it lives forever. Dyson worked through the physics in detail. He considered different types of life: biological, mechanical, electronic, gravitational. He calculated the minimum energy cost of storing 1 bit of information at temperature T. This is the Landau limit, kT log 2, where k is Boltzmann's constant. For computation at low temperatures, the energy cost per bit per operation drops towards 0, but so does the speed. Dyson argued that the limiting case is life that is fundamentally analog rather than digital, where information is stored in continuous variables rather than discrete bits. Analog systems can, in principle, operate at arbitrarily low energy densities without a hard quantum lower bound. Dyson concluded that an open universe need not evolve into a state of permanent quiescence. He wrote, "No matter how far we go into the future, there will always be new things happening, new information coming in, new worlds to explore, a constantly expanding domain of life, consciousness, and memory." The paper was hopeful, even poetic. It painted eternal life not as a triumph over entropy, but as a dance with it, slowing down but never stopping, thinking less frequently but never ceasing to think. Dyson later said the paper was a lot of unbridled speculation, but defended it as a serious exploration of the boundary between physics and biology. In 2000, Lawrence Krauss and Glenn Starkman published a rebuttal in the Astrophysical Journal titled "Life, the Universe and Nothing: Life and Death in an Ever-Expanding Universe." Krauss and Starkman pointed out that Dyson's analysis assumed a universe dominated by matter and radiation, without a cosmological constant. In a universe with a positive cosmological constant, a dark energy-dominated universe, the situation is qualitatively different. A cosmological constant creates a cosmic event horizon. Even though space expands forever, the horizon acts as a boundary beyond which no signal can ever reach us. The region of space we can interact with is finite. The number of particles within our horizon is finite. The total information accessible to us is finite. Krauss and Starkman calculated that in a universe with a cosmological constant, a quantum mechanical observer, one whose information storage and processing obey the laws of quantum mechanics, cannot perform an infinite number of operations. The reason is subtle. Quantum mechanics imposes a lower bound on the energy cost of each operation, related to the Margulis-Levitin theorem. Even if you slow down, you cannot avoid the fact that each bit flip, each logical operation, requires a minimum energy expenditure proportional to the operation rate. In a finite region with finite energy, you can perform only a finite number of operations before running out of energy. The argument also invoked the finite entropy of the horizon itself. The cosmic event horizon in a de Sitter universe, a universe where dark energy dominates and the expansion rate approaches a constant, has a temperature analogous to the Hawking temperature of a black hole. The horizon radiates. The total entropy associated with the horizon is finite, given by the Bekenstein-Hawking formula. S equals K A over 4L Planck squared, where A is the horizon area and L Planck is the Planck length. A finite entropy bound implies a finite information capacity. Krauss and Starkman concluded, "We find that eternal sentient material life is implausible in any universe." They wrote that Dyson's eternal expansion, which he found so appealing, is a chimera. Dyson responded. In a colloquium abstract archived by NASA, he wrote, "About 20 years ago, I published a paper in Reviews of Modern Physics entitled Time Without End, containing a lot of unbridled speculation concerning the remote future of the universe. I argued that it might be possible for life to survive forever. It is much better to be contradicted than to be ignored. I consider life to be analog, Krauss and Starkman consider life to be digital. The disagreement reduces to an unresolved question. Is life, at its most fundamental level, a digital process, quantized, subject to quantum lower bounds, or an analog process, capable of operating at arbitrarily low energy densities? If life is digital, Krauss and Starkman are correct, and eternal survival is impossible. If life is analog, Dyson's argument holds, at least in principle. The physics of consciousness and computation does not yet provide a definitive answer. This is the honest edge of the eternal intelligence question. We do not know if mind requires discrete quantum mechanical degrees of freedom, or if it can, in principle, be instantiated in continuous classical systems. We do not know if there is a hard lower limit on the energy cost of thought. We do not know whether the universe's ultimate fate, heat death in a dark energy-dominated cosmos, or recollapse in a closed cosmos, will even permit the survival of structures capable of thinking, regardless of how they are implemented. What we do know is that both Dyson's and Tipler's arguments rest on extrapolations far beyond tested physics. Both require life to control cosmic-scale processes. Both require intelligence to persist for timescales longer than the current age of the universe by factors of 10 to the tens, hundreds or more. Both assume the laws of physics as we understand them today remain valid across those timescales. And both ultimately encounter limits: information bounds, energy bounds, horizon bounds that may be fundamental. There is a separate strand to the complexity story, one that does not require far future speculation or cosmological eschatology. It asks a simpler question: is complexity increasing now, in the present universe? And if so, why? The physicist Seth Lloyd, working at MIT, approached this question by treating the universe itself as a quantum computer. In 2002, Lloyd published a paper in Physical Review Letters titled Computational Capacity of the Universe. Lloyd calculated the maximum number of operations the observable universe could have performed since the Big Bang, given its total energy content and the quantum speed limits. The result is a number: 10 to the 120 operations, performed on approximately 10 to the 90 bits if you count only matter, or 10 to the 120 bits if you include gravitational degrees of freedom. Lloyd derived this by dividing the total energy of the observable universe, about 10 to the 72 joules, by the minimum energy per operation given by the Margulis-Levitin theorem. The Margulis-Levitin theorem states that the minimum time per operation for a system with energy E is h over 4e, where h is Planck's constant. Inverting this gives the maximum number of operations per second, 4e over h. Integrated over the age of the universe, you get 10 to the 120 operations total. Lloyd also calculated what he called the ultimate laptop, a hypothetical 1 kilogram, 1 litre computer operating at the absolute physical limits. Such a device could perform 10 to the 51 operations per second on 10 to the 31 to 10 to the 32 bits. But it would generate so much waste heat, about 10 to the 32 watts, that its surface temperature would reach 10 billion Kelvin, roughly 100 times the temperature at the center of the Sun. the device would instantly vaporize any matter it touched and radiate a lethal flux of gamma rays. This is not a practical design. It is a statement about physical limits. Lloyd's figures give a ceiling. Any omega point, any far future superintelligence, any eternal computation scenario must respect these bounds. Tipler's claim of infinite computation at the omega point would require surpassing Lloyd's 10 to the 120 figure by an infinite factor. Ellis and Kuhl's objection was that the information bounds, Bekenstein, holographic, Busso, forbid this. But the more immediate question is not whether computation can become infinite, but whether it is systematically increasing in the present epoch. Here, the evidence is clear. It is. Consider the Chaisson ladder again, this time with the understanding that free energy rate density is a proxy for how much energy flows through a system per unit mass, per unit time. A star generates energy via fusion in its core, about 2 ergs per second per gram averaged over its entire mass. The Sun's core temperature is 15 million Kelvin. Protons fuse into helium. Energy diffuses outward over hundreds of thousands of years, eventually radiating from the photosphere. A living organism channels energy through biochemical pathways, respiration, photosynthesis, metabolism. A worm, consuming and oxidizing organic matter, processes roughly 10,000 ergs per second per gram. A human body, maintaining a constant 37-degree core temperature in a cooler environment, burning glucose to power muscle contractions and neural activity, operates at a similar rate. The human brain, specifically, consumes about 20 watts, 20 joules per second, in a mass of roughly 1.4 kilograms. 20 joules per second is 2 times 10 to the 8th ergs per second. Divided by 1.4 times 10 to the 3 grams, that is approximately 1.4 times 10 to the 5 ergs per second per gram. Chaisson's figure of 10 to the 5 is the right order of magnitude. A modern microprocessor, say a high-performance CPU in a desktop computer, dissipates 100 watts in a chip weighing a few grams. 100 watts is 10 to the 9 ergs per second. If the chip masses 5 grams, that is 2 times 10 to the 8 ergs per second per gram. If you narrow the boundary to just the active transistor regions, excluding the packaging and heat spreader, the density climbs to 10 to the 10 or higher. The trend is unmistakable. From stars to cells to brains to computers, energy rate density increases. Each step represents a new regime of organization. Stars organize hydrogen into helium and heavier elements. Planets organize elements into minerals and atmospheres. Life organizes molecules into cells. Multicellular organisms organize cells into tissues and organs. Nervous systems organize neurons into networks. Brains organize networks into cognition. Technology organizes matter into tools, machines, and information processors. At each level, the structure channels more energy through less mass. Chaisson argued that this is the signature of cosmic evolution, a progressive increase in complexity driven by available energy flows. The Sun provides a steady flux of low-entropy photons to Earth. Earth's biosphere absorbs those photons, uses the energy to build and maintain structure, and radiates waste heat to space. The entropy of the universe increases, but the entropy of the biosphere can decrease locally as long as the surroundings increase more. This is Schrödinger's neg-entropy feeding, made quantitative. But does the trend continue indefinitely? Can it? Here we return to England's dissipative adaptation. England's argument was that in a driven system, a collection of particles in a heat bath subjected to an external energy source, configurations that dissipate energy more effectively are thermodynamically favoured. The probability of such configurations increases. Self-replicating structures dissipate energy well because they create more copies of themselves, each of which dissipates energy. The system evolves toward higher dissipation rates. England's first experimental tests, published in Nature Nanotechnology in 2015, used the system of colloidal particles driven by an oscillating electric field. The particles were not alive, but they formed clusters that absorbed and dissipated the field's energy. Over time, the clusters evolved to match the driving frequency more closely, increasing their energy absorption. This was dissipative adaptation in action. But England was careful to note the limits. Dissipative adaptation explains why certain structures are more probable in driven systems. It does not explain the origin of heredity, how information is stored, copied, and transmitted across generations. It does not explain error correction, which is essential for maintaining information fidelity over many replication cycles. It does not explain compartmentalization, which isolates replicating systems from their environment and allows them to maintain internal conditions different from the surroundings. And it does not explain the genetic code, which maps nucleotide sequences to amino acids and allows the same informational polymer, DNA, to direct the synthesis of functional proteins. Dissipative adaptation is a piece of the puzzle, not the whole puzzle. It shows that thermodynamics favours complexity under the right conditions. It does not show that complexity is mandated or that it increases without bound. Prigogine's dissipative structures showed the same thing. A Bénard cell in a pan of heated water is a beautiful ordered structure. Hexagonal convection cells, each several centimeters across, covering the bottom of the pan. The cells form spontaneously when the temperature gradient exceeds a critical threshold. They are stable as long as the heat flow continues. But turn off the burner and the cells vanish. The order was not stored. It was not transmitted. It existed only as long as the driving gradient existed. Living cells are different. A bacterium can encyst, form a dormant, desiccated spore, and survive for thousands of years without external energy. When conditions improve, the spore rehydrates, resumes metabolism, and divides. The information encoding the bacterium's structure and function was stored in DNA, chemically stable, waiting. Life is a dissipative structure that constructs its own boundary conditions and encodes its own maintenance instructions. That is the step beyond Bénard cells. The question of whether this step was inevitable, probable, or a one-time fluke on Earth is unresolved. We have one example of life, Earth's biosphere. We do not know if life exists elsewhere. We do not know if the origin of life is a likely outcome of chemistry on any wet, rocky planet with an energy source, or if it required a rare confluence of conditions. We do not know if evolution toward greater complexity is typical, or if most biospheres stall at microbial mats. What we do know is that once replication with heritable variation exists, natural selection operates. Variants that reproduce more successfully become more common. Over billions of years, this process has produced organisms of staggering complexity. Eukaryotic cells with organelles, multicellular organisms with differentiated tissues, nervous systems with billions of neurons, brains capable of symbolic thought and cumulative culture. None of this violates the second law. All of it is paid for by exporting entropy to the environment. But none of it is mandated by the second law either. The second law says entropy increases. It does not say complexity increases. Complexity is what happens when entropy increase takes a particular route, one that involves self-replication, error correction, natural selection, and cumulative information storage. That route is narrow. Most possible configurations of matter do not lie on it. Think of the difference this way. Picture a mountainside covered in loose rock. Release a boulder near the summit. The boulder rolls downhill, losing gravitational potential energy, gaining kinetic energy, colliding with other rocks, fragmenting, dissipating heat. Entropy increases. The final state, rock fragments scattered at the base of the mountain, warmer than they started, is higher entropy than the initial state. This is the generic path. Now picture a different mountainside, one where the loose rock is not random rubble, but a carefully constructed set of ramps, channels, and levers. Release the boulder near the summit. It rolls down the first ramp, trips a lever that releases a second boulder, which rolls down a second ramp, and collides with a block that falls onto a platform which tilts and releases a third boulder, and so on. The system performs work. It routes the energy release through a series of controlled steps. Entropy still increases, friction, heat, sound, but the path is structured. The final state is not just warmer rubble, but rubble plus the result of whatever task the machine was designed to perform. This is the dissipative structure path. Life is a machine that builds copies of itself. Each copy is a machine that builds copies of itself. The machinery is encoded in DNA, executed by proteins, powered by ATP, and housed in cells. The process is not perfect. Mutations occur, and the imperfections are the raw material for evolution. Over time, the machinery improves in the sense that it becomes better at surviving and reproducing in its environment. Complexity can increase if increased complexity confers a survival advantage. But complexity can also decrease. Parasites lose genes, cavefish lose eyes, if simplification confers an advantage. There is no law of increasing complexity, only a ratchet that prevents information, once encoded, from vanishing unless it becomes costly to maintain. This is the modest, defensible claim. Complexity increases locally, temporarily, where conditions favor it. The universe as a whole is running down. Life is an eddy in the flow, spinning against the current. The eddy persists as long as the current flows. How long will the current flow? If dark energy is a cosmological constant, the answer is forever, but asymptotically weakening. Stars will exhaust their fuel. Galaxies will drift apart. The cosmic event horizon will shrink. New stars will stop forming when the universe is 10 to the 14th years old, roughly 10,000 times its current age. because the gas clouds that form stars will be too diffuse and too cold. White dwarfs will cool to black dwarfs. Neutron stars will remain. Black holes will dominate the mass budget of galaxies. And then the black holes evaporate. Hawking radiation, quantum particle creation at the event horizon, powered by the black hole's mass, causes black holes to lose mass over time. A solar mass black hole evaporates in about 10 to the 67 years. A supermassive black hole weighing 10 billion solar masses evaporates in about 10 to the 100 years. The timescale scales as the cube of the mass. By 10 to the 106th years, even the largest black holes, those that might grow to 100 trillion solar masses by accreting all available matter in their vicinity, will be gone. After that, the universe is a bath of photons and neutrinos, diluted by expansion to densities so low that particle interactions become exponentially rare. Entropy is near maximum. Temperature is near zero. This is heat death. The universe does not end in the sense of ceasing to exist. Space continues expanding, time continues ticking. But nothing interesting happens. No gradients, no structures, no thoughts. That is the forecast if dark energy does not change. If dark energy is weakening, as the DESI results hint, the forecast changes. A weakening cosmological constant means the expansion rate decreases. If dark energy weakens enough, gravity eventually wins. Expansion halts, contraction begins. Galaxies fall back together, space compresses, temperature rises. Eventually, a big crunch. The timescale would be much longer than the current age of the universe. Tye's model places maximum expansion at 11 billion years from now, and the crunch at 20 billion years from now. But it is finite. And if a big crunch occurs, does the omega point become possible again? No, not Tipler's omega point. The Ellis and Cool objections do not depend on whether a big crunch happens. They depend on the behavior of information and causality near the singularity. The holographic bound limits information density. Event horizons form unless the collapse is fine-tuned in a way that requires faster-than-light coordination. And even if horizons are avoided, a singularity with no horizons has zero area, zero volume, and zero information capacity. The infinite computation Tipler envisioned is forbidden by the same principles that describe black holes. But a big crunch does change the question from can intelligence survive indefinitely to can intelligence survive to the end? In heat death, there is no end. The universe fades into quiescence over infinite time, and any finite intelligence runs out of free energy eventually. In a big crunch, there is a definite end, a final singularity reached in finite time. Intelligence that survives until the crunch witnesses the end of space-time itself. That is not immortality, but it is something. Would intelligence want to survive to the end? What could it learn there? Tipler's answer was that the singularity itself becomes a computational substrate, that infinite information processing occurs in the final moment. Ellis showed that answer is wrong. But the question of what happens at the singularity, what the final state of the universe is, what, if anything, exists after the singularity, is genuinely open. Classical general relativity predicts that physical quantities become infinite and the equations break down. Quantum gravity, which would describe space-time at the Planck scale, does not yet exist as a complete tested theory. This is where the science reaches its limit. We can describe how the universe evolved from the Big Bang to the present. We can extrapolate forward using known physics and describe heat death or Big Crunch scenarios. We can calculate information bounds, energy bounds, and entropy bounds. We can model what kinds of structures could survive under what conditions. But we cannot answer the question of why there is something rather than nothing. We cannot answer whether the universe's low initial entropy was a boundary condition, a selection effect, or a consequence of some deeper principle we have not discovered. We cannot answer whether consciousness is an emergent property of certain kinds of information processing, or something that requires new physics to explain. We cannot answer whether the laws of physics themselves are contingent, could have been different, or necessary. Those questions stand outside the domain of empirical science. Not because science chooses to ignore them, but because they are not answerable by observation and experiment. You can construct metaphysical frameworks that answer them: theistic frameworks, naturalistic frameworks, idealistic frameworks. But those frameworks are not testable in the way a scientific hypothesis is testable. They are philosophical positions, and reasonable people differ. What the science does tell us is that complexity is not increasing everywhere, always, without bound. It is increasing locally, temporarily, where energy flows and where structures capable of harnessing that energy have evolved. The universe as a whole is moving toward maximum entropy. Life is moving, in some lineages, toward greater complexity. Both things are true. They do not contradict each other. They are two aspects of the same thermodynamic process. And that process, as far as we can measure, does not mandate consciousness or intelligence. It permits them, it makes them possible, but it does not require them. The universe could have expanded, cooled, formed stars and planets, and never produced a single replicating molecule. The molecules that did form on Earth, or wherever life first arose, were not pulled into existence by some cosmic attractor at the end of time. They formed because local conditions favored their formation. They replicated because their structure encoded instructions for replication, and they evolved because replication was imperfect and selective. That is the mechanism. It is elegant, powerful, and utterly indifferent to our presence or absence. Tipler wanted to prove that intelligence is mandatory, that consciousness is destiny, that the universe is structured to produce minds, and that those minds will endure forever. He built an elaborate mathematical framework to support that claim. The framework was internally consistent in the way a well-constructed logical system is consistent. But it rested on assumptions: a closed universe, controllable anisotropic collapse, the avoidance of event horizons, that are either contradicted by observation or physically implausible. And it ignored bounds, Bekenstein, holographic, causal, that limit what is possible even if the assumptions were granted. Dyson wanted to prove that intelligence could endure forever, adapting to an ever-cooling universe by slowing down but never stopping. His argument was more modest than Tipler's. No resurrection, no God, just persistence. But it too rested on an assumption: that life is fundamentally analog, capable of operating at arbitrarily low energy densities without a quantum lower bound. Krauss and Starkman argued that life is digital, that quantum mechanics imposes hard limits, and that in a finite region with finite energy, only a finite number of thoughts are possible. The question is unresolved, because the physics of consciousness is unresolved. What does it mean that both arguments, Tipler's infinite computation at the omega point, Dyson's eternal hibernation in an open universe, fail or remain unproven? It means that the evidence, as far as we can see, points toward an end. Not an abrupt, catastrophic end, but a gradual fading. Stars burn out, black holes evaporate, entropy approaches maximum. The universe becomes a cold, dark, dilute sea of radiation, and nothing interesting happens again. This is the conclusion the physics supports. The second law wins. Complexity is a transient phenomenon. Life, consciousness, civilization, all of it is a brief flicker in a universe that began in fire and will end in ice. This is the part that stays with me. Not the equations, not the debates, but the fact that